And so that's what I understand to be the nature of time. That's different than like what I would consider like common or even culturally accepted, where time is like a dimension you can move through it. You think about moving backwards from it,
Uh-huh.
left and right. Like it's its own independent dimension. When really, time is just a measure of change. It manifests because of change. If change were to cease, if everything were to stay on still, there'd be no time. Nothing would change. You'd be uh, frozen, I guess, in time in a sense. But there would be no time. So like change doesn't depend on time. Time depends on change. So it's like a causal reversal.
It was my great pleasure to interview Dan Harris. Dan is working on a theory that explains both time dilation and gravitational forces in terms of some very interesting causal effects. What makes Dan's paper especially interesting is that he's making inferences from ideas that I think can be known with certainty. A lot of the other guests I've had on this program have very intriguing hypotheses about the nature of the ether and how that might form a more rational theory of many of the physical phenomena which are currently understood with flawed theories, namely general relativity and quantum mechanics. But something that those theories lack is proof. They're really good hypotheses, they line up with the observations, but they haven't yet been proven. Something I find enticing about Daniel's work is that he has restricted himself to things that might actually be provable using premises that we already understand so far. So, a little bit about Dan before I show you the interview. Dan Harris is a causal AI architect for Northrop Grumman. He builds algorithms to perform tasks which would otherwise require human intelligence. His approach as a causal AI architect is to discover and leverage invariant correlations governed by causal laws between system inputs and desired outputs, which allow him to build causal AI systems that consistently perform well after development and are robust against various forms and degrees of noise. His notable achievements include recipient of the IEEE 2023 Industrial Innovation Award for Engineering and Implementing System-Level Discrimination in the Command and Control, Battle Management, and Communication System. He holds a U.S. patent. He's the author of Hyperdimensional Simultaneous Belief Fusion Using Tensors. And now he's turned that immense intelligence towards finding a more rational theory of relativistic phenomena. His paper can be found in the link in the description below. I give you Dan Harris. Welcome, Daniel. I want to start this interview, as I often start, by asking you about your motivation. So, what motivated you to seek a alternative to special relativity? Well,
So
not just special relativity, excuse me, both special and general relativity.
oh yes, yeah, of course. I didn't start with general. I started with special, and then I just saw to see. I wanted to see if it could extend to general, and so my motivation was to determine the cause of time dilation, and that stemmed from a project I was working on in artificial intelligence, and that's my background. I'm an expert in what I call causal AIs, AI systems that leverage causal information to achieve desired outputs from the known set of inputs by determining the causal relationships involved with the behavior that's desired. It's pretty robust against noise and things like that when you're able to do that. And I was trying to convince my company that like focusing on causal relationships instead of relying on models to set their parameterizations or learn their parameters like in machine learning or neural nets and things like that. Um, I felt like the my company should be looking at what made me successful in the past because I've built some very successful systems in highly competitive areas because of the time I took to look into the causal relationships and what's causing the system to make certain behaviors. Um, and so they're like, "Well, is this an algorithm?" I'm like, "No." And I was like, "Well, is can you demonstrate in recent discoveries of causal discoveries you made?" I'm like, "Well, just in the systems I made, but I can't really talk about that because it's you're not cleared to talk about that." But um, they're like, give me a use case. And I'm like, okay, a use case. I'm like, well, back in college, I was toying around with time dilation, and I watched like YouTube videos all the time on science, and I'm like, somebody, I think it was Neil deGrasse Tyson was talking about time dilation. It's like, well, we don't really understand the nature of time, and so I was like, okay, let me try this method I've been using, which I learned from Leonard Peikoff's book on logical leap. It was based off his classes on induction, and I'm like, let me see if I can apply these principles to time dilation. And I learned really quickly that this special relativity framework wasn't conducive to that because of their reciprocity principle. You can't just control the experiment because things are changing to, like, at a distance when you're changing your local settings. Like if you're changing your speed relative to something, well, that it's hard to say what's time dilated or not. And so I saw a new system from that. That's kind of what motivated me. It was like, okay, let's figure out a way that we can create a means to test the cause of time dilation.
Cool. Okay, I didn't know it. I didn't know it went that far back. So I find this kind of funny. They were like, so you're in your profession, your higher ups were not convinced of the power of identifying causes.
They have the same epistemological issues that the physics fields do. It's pervasive across the culture. It's not just isolated to physics.
I feel like that's especially bad because if you turn on YouTube and this is a side note completely, but like if you turn on YouTube and like look at Andrew Huberman, like he really focuses on causes. I don't know if he's always like truly identifying them. Maybe he is. I don't know. Watching his videos are like drinking from a fire hose. It's just too much information. But for all I know, he seems at least focused on whether he's succeeding or not. He's focused on causes. Like he even explicitly says, "Oh, it's very good that you're focused on mechanism," as he'll tell other scientists. And that's his word for cause and effect relationships, it seems to me. So it's not universal, this ignorance. Maybe it's just in the physical science, this ignorance of the power of causal relationships.
And I honestly think that it may be a limited understanding of causality too, because I think the common cultural understanding of cause and effect is temporal. This precedes that, this causes that, as opposed to like what Aristotle may have defined as causality, which is the law of identity applied to action. So there's two different, I mean, they're both true, cause, precedes effect, but that's like a very narrow and unuseful, uncausal view of causality.
That's probably why Huberman uses the word mechanism instead of causality, because like in his mind, it's not like he probably hasn't read Aristotle, like, so, or at least he hasn't thought about. I studied Aristotle at one point, but like he probably hasn't thought about exactly what causality should mean or whatever. So he's using the cultural words, but he's still figured out as a scientist. Oh, I need to figure out the entities and how they act, and what's his word? His word for that is mechanism. So that's really cool, man. That's a very first-handed scientific journey that started your journey. Sure. That's very cool. So
I didn't expect to necessarily succeed, but I was just going to give it a try.
Yeah, that's really cool. We've already talked about this, but tell us more. What is the philosophical and epistemological difference between your approach and the approach that led to special relativity? So let's focus specifically not on the difference between you and the culture. We kind of already covered that. But what's the difference between your approach to these issues and the issues that you find implicit in special relativity?
So I think one of the major issues with relativity and I guess most modern theories is that they use the hypothetical-deductive method, which rests a theory on a set of assumptions that aren't validated. And then given that those things are true, they're able to deduce these, very interesting and sometimes predictive things. But it amounts to trying to take, and I think this is the words of Leonard Peikoff, trying to formulate induction in deductive terms, which isn't possible that way anyway. And so what it amounts to is like a simple enumeration, which isn't a valid form of induction. It's where it's like you see a white swan, a white swan, a white swan, a white swan, and then I simply enumerated the ones I have. It's a white swan. Francis Bacon didn't like this, as you probably know. He thought it was childish because it's the simplest form of induction. It's like, well, induction is going from some instances to all. Well, here's some, therefore all, and it's too simple. It's not the correct way to validate your generalizations. And but to their defense, like there wasn't really a widely known method of induction to work. So like, okay, well, let's just take a stab at these generalizations and then deduce from there. And the reason that's necessary is because deduction requires one of their premises to be a generalization. That's like a given. And so if you can't validate them through means of induction, then, well, let's just try guessing and then seeing what we get. Versus the approach that I took was, well, I'm familiar with, Peikoff's work. I'm reading Ron's work. I'm going to be reading your work on induction. And so, I'm powered with some methods of induction that I know to work, Mill's method being the main one, tied to Ayn Rand's theory of concept, which is another one. And so I was able to look out at reality and see, using a proper method of induction, induce the generalizations that I use to then deduce from. So you got to set a relativity theory based on its foundation, guess, not validated, and you have, I guess, the theory that I developed, which is founded on a principle that was induced. So there's just two different approaches to getting your foundation and then deducing from it.
Wow, that's I really like that answer. I think my theory of induction would have a lot to add to your answer, but that's and you'll learn all about that soon enough, or maybe you'll disagree with it. But I really appreciate your first-handed approach to all of this. That's I was not able to have such a first-handed approach when I was in college, simply because I was overwhelmed. There was just too much. There was just too much to take in. And yeah, I just didn't. I actually didn't question physics too much in college, believe it or not.
They gave you these generalizations, and then they told you how to deduce from them. They didn't really explain how they came about.
I didn't even pick up on the fact that they were doing that. I thought that they were I thought that the math I was looking at on the board somehow proved it, and I had this sort of default inductive way of thinking about proof. And I knew, math on its own can't prove anything, but all this math that the teacher's writing on the board, it must have something to do with the observations. I just have to see how the observations lead to the conclusions in this math. And of course, I was searching for that in vain, thinking that it was my fault that I couldn't see it. But it didn't take, by the end of college, I noticed oh wait, I started getting the sense my classmates certainly don't understand this. Does the professor? What happened if they don't, so that was the kind of thinking. Now, so let's start getting into your theory. I think one of the main things that leads you to your different view is your view of time. So before we get into the details of your alternative to relativity, tell me your view of time and how it differs from mainstream physics.
Sure. Time is by no means like the foundation, but it is an important concept.
It's one of the important ones I want to set the audience up with, because I think you're right. It isn't fundamental. Well, it's one of the fundamentals. Let's start there. And I think the audience can really benefit from your very clear view of the right view of time.
Oh, sure. Yeah. So one of the things that I had implicitly understood was I think a better understanding of time than what was within the framework of relativity. And so it took me a while to really draw it out, and I actually had to search across my resources to look at historical definitions of time. I think Einstein defined time, at least in one conversation, as that which clocks measure, which it's circular, right? Because I think he was trying to be funny. I don't think he actually like intended it to be like a circular argument. I think he was just trying to show that it's very difficult to define what time is.
Hmm.
Because if clocks measure time, then what is it that clocks are measure? Or if the things that measure, or the things that clocks measure is time, then what is it that clocks measure? It's like it's very circular. So
Yeah.
I finally stumbled across a definition. It wasn't mine, but it lined up with my understanding conceptually of what time was, and that is the interval over which change occurs. And so
Yeah.
I it gave several. I looked at through several examples of timepieces. Okay, now let's look at what clocks measure. Is it this thing, the interval over which change occurs? Is that what clocks are measuring? And sure enough, every instance of a clock is measuring some interval over which change occurs. And if it's regular, the better. And the shorter the period, the better. That gets you more precise intervals over which change occurs. And so that's what I understand to be the nature of time. That's different than like what I would consider like common or even culturally accepted, where time is like a dimension. You can move through it. You think about moving backwards from it,
Uh-huh.
left and right. Like it's its own independent dimension. Really, time is just a measure of change. It manifests because of change. If change were to cease, if everything were to stay on still, there'd be no time. Nothing would change. You'd be uh, frozen, I guess, in time in a sense. But there would be no time. So like, change doesn't depend on time. Time depends on change. So it's like a causal reversal in the sense of how
Yeah.
people are thinking about it.
Yeah.
And
Yeah, that's very important.
with time, I was going to explain where I thought the idea of a dimension of time came from.
Oh, yeah.
So like,
So yeah, where do you think this weird notion of time is a dimension? I think in a certain sense it is, but it's not. It's treated as I think tell me if you agree with this. In the culture it's treated as though it's interchangeable with the spatial dimensions.
in a
And
lot of ways, yeah,
I think
yeah,
that's really the problem because if by to me the word dimension means like quantitative characteristic that is distinct from other quantitative characteristics. So to me, color and temperature can be thought of as dimensions in an extended sense, but certainly
orthogonal
not
measurements or
spatial.
anything. Yeah,
Exactly. Orthogonal measurements, that's what I mean by unrelated to others. Like you can't add the
yeah,
temperature to the color and get something. So like that's what I think of as or yeah, but anyway, go on.
yes. I mean, I think Newton was the one that tried to create this universe where this backdrop was space, and then you had this fixed time. And I don't think that that's exactly accurate. I think it's useful for deriving mathematical relationships, and so in some sense there is an orthogonality of time in that way. Um, but then you get like these weird symmetries where things going forwards and backwards in time, like trajectories, they would follow the same path backwards in time and forwards in time. And so people start getting this idea is like, well, what if I just turn the time knob backwards? Another possibility where it could have came from is like a hasty generalization, in a sense that if time is the interval over which change occurs, hypothetically change could happen anywhere. Therefore, this interval could happen anywhere. Therefore, time could be anywhere. Time doesn't really exist where change doesn't. So you have to have some relationship to change to understand and measure time.
Right. Yeah, one of my favorite ways of thinking about this is like going back in time makes no sense. So like what if you
No.
went back in time to World War II? Well, what would that actually mean? That would mean like some the only way I could think of that actually happening is if some wizard or alien moved all the matter around, reconstructed Hitler, reconstructed General Eisenhower, put everything back together, and then you had World War II going on again. But then it's like, well, you didn't go back in time. It's just that World War II is happening again now.
Yeah.
That's all that's what's going on. Everything changed back to being World War II.
Yeah. When people think of time travel, they think the entire universe going backwards in time. But
Right.
in this mechanistic view where time is the measure of change, you would have to be omniscient, omnipresent, and all powerful, because you would have to
Right.
be at all the locations and immediately at the same time reverse whatever it is that was at that location, and then you'd also have to reverse the mechanism that reversed it as well. So like it just I don't, and then at some point you'd have to stop the reversal once it's reversed, and so it's just not feasible to do any type of time travel at all.
And
So
then even after that, it still wouldn't be time travel. It would just be a massive change to existence.
right, yeah, you would be in a state of existence that had existed earlier, but now it's not it would be in the future. You know, it's just yeah. I mean, this kind of ruined time travel movies for me, but
Yeah, right.
it's still fun to like suspend belief and like, okay, what if you could? You know,
Yeah.
you have to really suspend the fact that you can't really do this, but what if you could? It's a fun
Right.
thing.
Right. Well, there'll be plenty of other cool sci-fi that will come from an actual understanding of what's going on in physics as opposed to a fantastical understanding of physics.
Yeah. Always.
Let's see. So, okay, now you also have this principle of eternal simultaneity, which I find very interesting, about that you presented at the beginning of your paper. Tell us about that.
That's actually the fundamental. That's the foundation. And that's the induction that was made. And I'm not actually sure if it's even an axiom in a sense, because any attempt to disprove it, I've found that requires some, like, making the argument in the present or having the argument being brought up in the present and thinking about it in the present. But it's the notion that everything everywhere exists now. And so the present is all that's present. And it's based off the induction that when you look at all the evidence, every single observation, it's universal without any counterexample. So there's no exception to this. All measurements, all events, all in the sense that like all things that you observe, all interactions that are happening, even when you reference a memory that of the past, you're doing it in the present. Whenever you're projecting out into the future, you're only using what's available to you in the present and the existing models to project. Everything is happening in the present. There is no exception to this. There is not one shred of evidence to suggest that things don't happen in the present. And this gets into the point where like to consider otherwise becomes arbitrary. And so we're like, well, what about this relativity simultaneity? It's like, well, if you look at what that depends on, you go back to the epistemological root. It's based off of a postulate, which is an assumption that hasn't been validated. And so you have all of this evidence, all of it, versus this conclusion from a postulate which hasn't been violated. And
which hasn't been validated.
Excuse me, yes, hasn't been validated. And so, you have to be the judge for yourselves as rational beings, like which seems to be most rational to believe that, everything that happens is in the present, because, that's what every piece of evidence is consistent with, or that the present is relative. So, like, if you have, let's say, three entities in the same location, this is like this is a play off of the Andromeda paradox. They could have a slight relative motion. And actually, let me draw this. So I'm going to create a space-time diagram. Okay. All right. So you have time, space. Okay. And this is just one inertial frame. Okay. When you look at, and this will be one person's inertial frame. So like this space axis is the person traveling along this time axis, I guess. So he's not moving in the spatial. That's his present horizon. That's his present. But if you have another guy that's like traveling this way, and this isn't to scale, like I'm not making 45 degrees of speed of light, but I'm just showing as an example. His present looks a little bit like this. So what he thinks is present is across this line, and it has to do with the fact that he's assuming the speed of light is constant. And if the speed of light is constant, then things reach him like that as the present.
Yeah, right. So and to make a comment on this, this is part of the framework in special relativity that is an unconfirmed result of the hypothetical-deductive method. The reason
They
that
can't
we
confirm
accept,
that. Yes.
yeah, the reason that, I mean, there's a sense that it's confirmed, but it's this loose sense in which when they assume it, it gets the right result. But of course, there's all kinds of other assumptions that also get the right results. Dialect pointed
Right.
this out in one of his videos, that there's a completely different framework where you can preserve. Actually, tell me if you've seen this video, because you'd love it.
I've seen
Because
all of his videos.
okay, so there's
Excellent YouTube channel.
they're great videos. So there's a video where he talks about an alternative. I think he calls it matrix theory, which is a little, I don't know, it's a little whimsical, but so he calls it matrix theory. And the idea is that for different observers, you choose a different fundamental value of epsilon, I think. And on what basis do you do this? You choose an epsilon so as to preserve your principle, which is this universal sense of simultaneity. And it still gets all of the same results. It gets all of the right results when you do this. Do you remember this? It involves
results.
What's that?
Yes, the verifiable results are the same. The unverifiable
Yeah.
ones are not. So
Right.
you'll get the same observations, and that's all we have are the observations. Those are above reproach. My measurements
Yeah.
took this. Now, why did your measurements take that? That depends on your model. And this model says that, well, my measurements took this because the speed of light is constant for everybody in inertial frames, and that means that has a consequence of these simultaneity lines being different. And so they'll say, like, there's one entity, let's say it's traveling in this direction as well. So the green guy here is saying that this, let's say it's a flower, all right? So you have a seed down there for the green guy. You have a actual flower for the guy that's in the blue line. And then the pink line says, well, it's ash, it's dead, right? So the same entity simultaneously at this location is in 3 different states. But then when you bring back the fact that, well, eternal simultaneity, all evidence suggests that things are present right now. Like, you have 0 evidence to suggest that 3 existences of the same entity exist at the same time. There's only ever one existence of the entity. Whenever you're taking any measurements of it nearby, like you're there, like there's never 3 flowers. It's only ever a seed, a flower, and ash at one instant. There's not all 3. So it's a very interesting concept. Like I can picture it happening, but at the same time, like when I look at my evidence, there's 0 evidence that this flower was ever 3 things at the same time. So
I mean, well, it's more than that. It seems to be a contradiction. But let me parse that, because I'm not. I definitely disagree with special relativity, but this notion that there could be a different present for different entities is not. I don't think that's actually contradictory. Let me run through all of this. So first of all, yeah, I agree that relativity did not make its claim that the speed of light spreads isotropically, that light spreads in the same speed in every direction, and therefore this sense of differing simultaneities. I don't buy it. Okay. Let me go on, and then I'll also say that everything you said in principle about things existing in the present. Well, I don't know. I'm not sure if I agree. Let me move on to my next point where I object here. When I think of what the present is, I'm working on a hypothesis of what I'm working on, trying to understand time, and I think you very clearly understood the fundamentals that, and I agree with them. It's the interval over which change occurs. Mm-hmm. Okay. But I guess my perspective it attempts to go deeper. I would say, what is this interval you're talking about? What do you mean by interval?
That's a great
question.
I'll pause
my yeah, what do you think the answer to that is?
So Well, if you're left with eternal simultaneity, where there's only one plane of existence and that's it, you still have to make sense of the fact that existence in this moment wasn't the same as before. Like there's things are changing from one moment to the next, and so time then becomes a measure of this change. There was I forget exactly who. Somebody mentioned that like if the length scales all changed simultaneously, like if everything like a yard became 1,000 yards, and at every moment and all the relative distances change with it, like I don't know that we would notice that.
Right.
The same thing kind of goes for time.
Mm-hmm.
If the interval of this change in this plane of presence were to shift, like if the second became 1,000 seconds, like I don't know that we would notice.
Well, let's be clear. If this were to happen, it would be like a time travel sort of deal where a wizard or powerful alien changed every single entity so that its durations took 1,000 times longer each. If that happened, is what you're saying, right?
Well, in a sense, it does happen locally for time dilation, because
Right.
because as the internal mechanisms of things might slow at the same rate, but if they all slow, you won't notice it. That's why time dilation isn't possible to detect directly, because even your brain and your experiences and like your neural processes, those are all physical, and so their slowing would in pace with everything else would make things seem like they unchanged temporally. So it's an interesting concept for sure. So go ahead with continue with your theory.
Yeah. So when I think it's the interval. I didn't hear an answer to my question there. What do you take the interval to be?
So the interval it's always in comparison. So measurements.
Okay, good. Yes,
are
it's always in comparison.
Measurements
Yeah.
relative to a standard. And so what is it that
Yeah.
like? Ron does this very good in the book, and I haven't finished it, but I like this chapter, where you have to select a standard, and the standard has to have a purpose. And so the interval of change. So like you're always comparing, let's say, the tick of a clock that is very regular.
Yep.
That interval of change relative to these maybe irregular changes, like something that doesn't exactly happen, time to time.
Yeah.
And
So
you
I
can
think
you can say, I'm going to take 10 minutes to grill my steak, and know reasonably well that that's going to be cooked to your liking, because you've done this number of times where you've measured how long it takes to cook the steak at this temperature relative to the ticks of the clock, and so it takes that long. If everything was retarded, like in time dilation sense, it would still take that many ticks of the clock, because it takes the process mechanism that many evolutions, to reach the desired cooking status of the steak.
Yeah, it's the duration. So this is really good. So when we say interval over which a change occurs, when we say an interval, we're actually referring to a whole nother change. So I'm spitballing this right now. Usually I try to come up with stuff like this, slowly and carefully on my own, but just doing this live, I want to say that time is like relative changes between interacting entities. Relative changes between interacting or potentially interacting entities, something like that. So let me illustrate what I mean. So this is really just the same as what you just said. I'll just elaborate on your steak example. The steak is going through a process of change. Mm. The clock is going through a process of change. The clock is just this uniform, easy to understand, consistent process of change that we use to measure other processes of change. And by the time let's say it's a stopwatch for simplicity, by the time we get to by the time the hand moves to 10, the steak is done. The steak is at the desired level.
With variation.
With some variation.
There's a reason why we don't use steaks as measures of 10 minutes.
Right.
If you cooked it to the same state every time. It would vary from like 9 point something minutes to
Yeah.
10 point something minutes. And so that's why,
Right.
when you do 10 minutes, it's like it's going to be within your liking to some variation, for sure.
Right. Right.
Which makes
Yeah.
clocks
So
better clocks than steaks.
right. Yeah. Right. It's not a uniform process of change.
Yeah.
Good. Now, so in that earlier sentence, I said by the time the clock gets to 10, the steak is done. I used the word time there. I'm being a little circular. What can I do to eliminate that circularity?
However many ticks of this, hand
The
going
way
around.
the way I would put it is this. The clock is acting on me in a certain way. It's giving me light that shows a 10 on there. Okay? To put it simply. I'm using when, but
The moment that happens.
I'm trying to explain time in terms of other things. So words like moment and when are off limits.
If the present is an axiom, you can't escape it.
That's kind of what I'm contesting. I'm wondering if time can be broken down into language involving change alone. Because we already acknowledge that time arises from change. And if that's the case, I wonder if we know enough about existence to explain time entirely in terms of its causes, entirely in terms of change and its properties. That's my
Let me
ambition.
take a stab at this.
Okay.
So there's a reason why this conception works, and you have to look at the facts of reality. The first fact of reality is while the present is evolving, you can't have the prior evolution and the next evolution exist in the same moment. That would violate identity.
Uh-huh.
Okay? And so there needs to be some interval between the two, and that's what time is. And it also ties into causality this way, and that is when you recognize things act in accordance to their nature. What that means is, given the same conditions that in which you initiate the causes, the same effect is going to transpire. And so the clock has more regulated conditions that you're repeating over and over and over again. The steak, you don't. The steak has different thicknesses, maybe widths, maybe it's a different marbling. And so there's just these subtle differences that regulate, once it reaches, let's say, medium rare perfectly. The differences in time are there. Whereas for a clock, those mechanisms are very much like the same essential conditions every single time. And so it's like almost like it's a recognition of causality. Given this identity of this thing, and given the same initial conditions, you're going to have the same result. So we want to know from instant A to instant B, this evolution, this interval between them. We need to make sure that this interval is the same every single time. Then we need something that is the same conditions every single time, something we can control really well. Even atomic clocks, being one of the more precise time instruments, isn't infinitely precise. There's some drift over millions of years, like there's like a second drift, but still, but it's as good as we've been able to achieve on that scale. So we got to like the pico or the atto time clocks that we're starting to develop. So I'm trying to address your question about this, and it's really, I think, a matter of recognizing causality, where this notion of time comes from. So as things act, they can't exist in two different states at the same time. There's some interval. That's where this is time.
And that interval will be the same so long as the causes of the process of change are the same.
Yes.
Yeah, I think that's true. I think all of that's really true. Here's the direction I was going with all of this, which calls into question the idea that there's some kind of like universal present. See, I generally think that the concept of the present only applies locally.
Right.
And
said that
incidentally, Ayn Rand thought this too. See, Mom said.
Yeah.
So, but yeah, not that that's an argument, but like it's. I think Rand somehow was aware of this. I'm not just through observation of reality. But here, well, I can kind of see how she would get it. So here's why I think the present is a local phenomenon. When we're talking about the present, well, let's go back to what I said before. When we say that the steak is done after 10 minutes, we're saying that the watch acted on me when it was in a state of reading 10. That is, it showed light to my eyes. The steak acted on me when it was in a certain condition of medium rarity. Okay? So we say that these events were simultaneous. Okay? The standard of simultaneity is that both objects going through a process of change acted on me at some point during that process of change. The clock didn't act on me at 11 or 9, it acted on me at 10. The steak didn't act on me as bloody or shoe leather, it acted on me medium rare. So it's so as a result we say the 10 and the medium rare was simultaneous. Now, entities can only act on entities that are next to them. That's the principle of locality. And as far as I know, there's no exceptions to that. Entanglement might be an exception, and then we can talk about maybe talking about a non-local sense of the present. But because simultaneity has to do with action or the potential to act, I am not sure if it means anything, or I'm not sure exactly what it means to talk about what's going on right now and in Alpha Centauri right now.
So I think you're bringing up there might be a metaphysical and epistemological difference.
Okay.
In terms of significance. So metaphysically, if you believe there's a preferred frame, then simultaneity is part of that framework. If now epistemologically, you may not know which frame is preferred. You may not know where simultaneity resides. You may not know which of these simultaneity lines is correct. It may not be any of the three. There might be a fourth one that is going to be the simultaneity line. And so, I think there's certainly something to say, well, we can't really talk meaningfully about what's simultaneous at a distance because we just don't know. And it almost doesn't matter because what that happened then, whenever it happened relative to my simultaneity, it happened in such a way that that effect reached me maybe at the speed of light now.
Yes.
And so I'm interacting with physical traces that were left behind entities really far away, especially when you look at the night sky, billions of light years away. They're now affecting me now. But those physical traces exist now in the present, in my present.
Yes.
When they were radiated, I don't know. That doesn't take away from the fact that you can still be certain that it radiated at some point.
Yeah, but if you it radiated at some point in its it radiated at some point in its own present, in the present for the Alpha Centaurians. Now, there's an extended sense of the present we can use. We can say Alpha Centauri is 4 light years away. I'm looking at it. I'm seeing what happened 4 years ago for it. Why? Because I know it took the light 4 years. But now we're
actually don't know that.
Oh, why not?
It could have taken less time. It could have taken more time. So
but we think right, because we don't know the true speed of light. So we don't know the true speed of light. So yeah, oh man. See the fact that we don't know the true speed of light is tangled in with this issue of simultaneity in two ways. In order to measure the speed of light, you need like a definition of simultaneity, right? and then it turns out that any attempt to like define simultaneity ends up being reliant on this speed.
Yeah.
Yeah, holy moly. Okay. It looks like you already knew that. That's a really cool thing to realize. That's really cool. I kind of already knew that. I just never said it that clearly before, but yeah.
We say it takes 4 light years, because if you were to, shine light there and have it reflect and come back, it would take 8 years to take the average.
Right.
But it could have been faster that way and slower towards us, or vice versa, because we're moving through a preferred frame.
But my point is like, even if we somehow knew this, I don't even think it makes sense to talk about it. Like, the present just doesn't apply to what's going on in Alpha Centauri. The present applies to the piece of ether that's acting on my eyeball right now as a result of the propagation of action from Alpha Centauri to here.
Okay. Yeah, I want to make it explicit that while the ether is something that is likely to exist, it's not part of the theory we're talking about. It doesn't rely on ether existing. It just relies on a preferred frame, which is founded on, or deduced from, the eternal simultaneity.
Right. We'll get to that in a moment.
But we can talk about the ether as synonymous with a preferred frame.
Well, yeah. We should have a discussion on whether that's a good idea or not. Because I think your theory. Let's talk. I think we can. I've said what I wanted to about time. Have you said your piece about time? We'll move on to the actual theory of simultaneity.
Could say, yeah, you covered it.
Yeah. What's that?
You covered all the things I probably could say on time.
Okay. Yeah. So I like that doesn't get what I've said. Doesn't get us that far, but it gets us to the point where we just really. I feel like that leads somewhere else, but I'll stop for now.
Am I good to erase this?
Yeah.
Okay. I'm glad I used the board.
Yeah.
Useful.
Okay, so let's get into the theory itself. So tell us how you identified the cause of tell us how you used Mills methods to identify the cause of duration dilation. Notice how I insist on calling it duration dilation, because it's the duration of specific processes of change that are changing, not time itself.
Yes,
although maybe with a
talk about it.
Yeah, maybe with the appropriate understanding of what time is, time dilation is fine as a term. But until I think that through, I'm going to call it duration dilation, because then I'm sure that I know what the hell I'm talking about.
Yeah, so it's always a choice whether or not to keep the label and fight for a better meaning, or choose a new label like this. As long as we're talking about the right concept, which duration dilation is fine. It's a very good thing about it. So the Mills method I used, once you have a preferred frame, there is no reciprocity principle, and so you can really fix your thought experiments. And once you have a preferred frame, by the way, Lorentz ether theory becomes a huge mechanistic framework which you can rely on. It was founded...
Tell us real quick, remind us what the reciprocity principle is.
So the reciprocity principle under relativity is basically stating that no inertial frame has a rightful claim to say they're the preferred frame. And so if you have relative motion, it's equal to say, no, you're in motion, and the other guy says, no, you're in motion, I'm stationary. And so you can derive the laws of physics the same from either frame. When you have a preferred frame, the laws of physics are not reciprocal across frames. There's a preferred frame in which laws of physics apply, and then according to Lorentz ether theory and the theory universal specificity, which is the name of the theory, the name for the theory I've developed, they both agree that it's just a matter of distortions in your measurements that become miscalibrated. And so that's anyway. So once the reciprocity principle goes away, so you have like a fixed frame from which the laws of physics apply. That's the frame you use to apply your thought experiments. It's hypothetical. We don't know which one it is, but you're assuming this is the, when you draw out your, okay, thought experiment, this is my fixed frame, okay, for time and space. Now,
the frame itself isn't hypothetical in your view. It's that we simply don't know which one it is. We know that there is one in your view. We just don't know which one it is. Yeah.
And so it's important under Mill's method to list the plausible causes and then go through controlled experiments, each one, and rooting them out through method of difference and method of agreement. And so the plausible causes for time dilation. So you have basically the time dilation being the uncalibrated duration measurement versus the calibrated duration measurement. So your instruments are distorted in this one, and you think this is your measure of time, like in the twin paradox, where one twin goes away and comes back. The twin that aged less, he says, well, only 10 years or 2 years elapsed. Well, that would be your distorted measurement. And then the twin at home says, well, 10 years has elapsed, not 2. And that's your calibrated measurement, let's say, assuming the Earth was in the correct preferred frame. And so you have, I came up with a couple of velocities. So I have relative velocity between objects. I have a velocity in the preferred frame. I came up with acceleration, big W work, and then little w specific work. Work being like the ability to do like a measure of energy. Like energy is the ability to do work. Work is like a transfer of energy. Specific work is this transfer of specific energy of some nature. Acceleration, there was one point where Einstein thought that maybe general relativity could explain the twins paradox at the point of acceleration. And so I thought that was plausible. We should test for that. The velocity in the preferred frame, because if you look at the time dilation equation, which is, let's name this 1 over gamma v for now. So 1 over gamma v is equal to the square root of 1 minus v in the preferred frame squared over c squared. C squared. Okay. And this is the speed of light in the preferred frame, and it's isotropic in all directions, only in the preferred frame. And then you use Newtonian mechanics to figure out what it is relative to a moving object within that frame. Okay, so these were all the variables that I considered. And speed is another one. But
these are all the causes of duration dilation that you considered.
Yes.
Yeah.
And I considered speed as well, but speed has a causal relationship already with work, specific work. So these are interchangeable. And so I had to come up with thought experiments in which,
because specific work is just motion. It's basically work divided by the mass of the object getting worked on. So it's specific to that object. It's not dependent on mass.
That's right.
And the reason that it's interchangeable with the velocity in the preferred frame is because specific work basically refers to a change in velocity, which would include a change in velocity with respect to the preferred frame.
Yes.
Yeah.
So I went through these one at a time, coming up with thought experiments that would rule them out, and found the one that was consistent with all of them. And so for ruling out relative velocity, it was very simple. I took this space-time diagram for the preferred frame, and I considered 2 objects in relative motion going this way, and the same, let's say, speed profile in opposite directions or some other tangential directions, and then coming back together. Okay. And at no moment was their relative, let's say this guy's 1, this guy's 2. So if you look at the measure of dt1 versus dt2, it was always unity, so it never changed. So you have no relative time dilation affecting the objects because they're in relative motion. So relative motion is not the cause of time dilation between objects. That's what we're
because there's a case. Couldn't we say that the amount of duration dilation of the 2 objects was equal, and therefore the comparison was, so there was duration. You could argue that there was indeed duration dilation, but
this is answering a different question. duration dilation one object relative to the other, which is what relativity believes. Any relative velocity between objects is going to cause time dilation between the two objects, like one measure of time versus the other's measure of time, or one's measure of duration versus the other measure of duration. So here's a case where they have any amount of relative velocity from 0 to the speed of light times 2, I guess, because they're going in opposite directions at the speed of light, maybe. Where they go away, come back, you measure what happened in terms of their estimates of duration change, and it's identical. The first object and the second object measure the same duration. There's no relative duration differences between the two. So I was able to rule out relative velocity from that thought experiment. Okay. So,
I just wonder if someone could say that, like, they're well, maybe I'm making your point. Maybe I'm making your point for you, that, like, I'm imagining what someone from the perspective of special relativity would argue here, and they'd say, well, but both objects simply had the same amount of time dilation, which is why there's no difference. But that implies that they're moving with a preferred frame to cause the same amount of time dilation for some reason other than relative motion. Another thing worth noting is that, like, relative motion with respect to what? With respect to what other object? There's a multitude of different objects you could be talking about there. Yeah. And this shows that for one particular other object, there is no time dilation. For other objects, there would be this relative time dilation, but for these two, in comparison to one another, there isn't. So you can get the time dilation without relative velocity, is your point?
Yes.
Okay. Yeah.
So this experiment also disproves velocity relative to a preferred frame, in the strict sense that you're taking into account both direction and speed. So you said we kind of tacitly assumed we were talking about speed when we said, well, they both have the same velocity. Well, they actually don't. V1 is equal to negative.
Yeah, they have opposite velocities.
So V1 does not equal V2 because of the sign, right? And so this shows that through the method of agreement, where they both exhibited the same time dilation relative to the preferred frame now. So this is the same for both of them. But they had different inputs that we thought was causal. So that demonstrates that this is not the cause either. Which makes speed, aka specific work, a really high candidate at this point. But let's take a look at I've looked at the others as well, and for this to work, I took a very similar experiment. Well, I only took half of it, let's say. Okay, and in this particular experiment, there was a guy that was in the preferred frame, right? And for acceleration, I just basically created two spaceships. One that starts at a velocity down here and continues on forever. And then there was another one that started down here and continues on forever. And when this spaceship, let's say, meets up with the observer that's stationary in the preferred frame, they do a synchronization. That's time 0, t0. Okay. This spaceship coasts, right? So continues to coast until it gets to this point, at which point there's another time hack. We'll call it T1. Okay. And then at the very end, T2, right? That's in terms of this spaceship was coasting, it synchronized the time. So whatever time passed for this spaceship from T0 to T1, that time passage was passed on to the second spaceship, which then carried on coasting to the original observer, at which they finally compared the clocks. So in this example, there was zero acceleration, right? So in both the guy that's sitting still and for the clocks that were moving here, there was zero acceleration for both cases. So this is a method of difference where the time dilation measured for the moving clock was less. So like this, let's call this one 2 and this one 1. D2 times dt was less than dt1 over dt, which this one was actually 1 unity. There was no time dilation for the guys stationary in the preferred frame. And so neither one of them accelerated. So the inputs, the acceleration was the same. So if it was the cause, you'd expect the same output, which you don't. There's a difference in time dilation, the measure of duration between the two cases, even though acceleration was the same. So this ruled out acceleration.
So what I'm gathering from this is that a difference in velocity is associated with a difference in velocity of two bodies with respect to something. Forget about the preferred frame for a second. Is going to lead to a difference in the internal rates of change.
Yes, I think so. I mean,
that's my way of thinking about it. I'm getting rid of the preferred frame. I know you're keeping it here, but to me, I'm trying to get to the reasoning that would cause us to accept a preferred frame. And what I said is true, and I think it leads to a preferred frame, even though I'm remaining agnostic about it right now.
Right. So, I'm acknowledging that ether could be the reason for a preferred frame, which I think is what you're kind of inching towards.
That's not what I'm inching towards right now. Right now, I'm insisting on being conservative and saying, hey, forget about the ether, forget about a possible preferred frame. What we're seeing here is that two objects, the one traveling to the upper right and the one traveling to the the one that's stationary in this frame, in this green frame, the one that's stationary, number one, the green object now, it undergoes different rates of change than the two objects that cross paths. Basically. Those two objects are moving, and their clocks run slower.
Yeah. I mean, this experiment also works.
They run slower than the one. They run differently anyway. We don't know which one's the preferred frame, so they run differently. There's the difference in speed leads to a difference in the rate. We don't know because for all we know, the ether's friggin' running along with the one of the diagonal ones. For all we know, the preferred frame's running along with one of the diagonal ones. For all we know, forget about the preferred frame. This just shows us that a difference in speed from someone's perspective leads to a difference in duration, as measured by some kind of clock.
Not precise enough. You can have a case where that was the first case where they were actually going in opposite directions in the preferred frame. So they have a speed relative to each other that's changing. But their duration measurements are not. So you just have to be careful with the precision is all.
So you're saying my formulation took us back to the idea of relative motion causing time dilation. I don't think it did, but let's continue. Let's continue with what you're saying here.
So the work, I like taking things to extremes to disprove things when I can. So for work, I considered the planet Jupiter. And it's let's say we applied enough force to accelerate over some distance to accelerate it to 1 centimeter per second, right? And then you took the same amount of work that went into Jupiter and you do it to a marble, and it probably would exceed the speed of light. So, I mean, in a sense, it's probably not possible to exceed the speed of light. So its relativistic mass would have increased and whatnot, but it would have gone to a much higher velocity. And so they would experience a difference in time dilation, even though the same input, the same amount of work was put in. And so that eliminates work. And then we're falling back on speed, which is basically tied to specific work. And if you look at the equation here, this is like a dot product, right? And so it's implying that it's speed, its direction doesn't matter. But at the same time, this is also let me think. This is also, let me erase all this and actually let me draw the triangle I was talking about. All right. So this is actually, if you can rewrite this in terms of specific energy, and so it becomes 1 minus 1/2 Vp squared over c 1/2 c squared.
Mm-hmm.
All right, and the reason this is Newtonian mechanics. So specific work is defined as the integration of your acceleration, some direction, over some distance.
Yeah.
That's the definition. And when you do like the change of variables in the calculus, it becomes 1/2 v squared. So
Yep.
that's like it was there the whole time, and in the sense of like the specific work was present in the formulations that give you accurate descriptions the whole time. It's just been kind of concealed.
It's been
mostly.
implicitly canceled.
It's been concealed because nobody's I guess been able to look at the cause of time dilation because of the reciprocity principle. So it never occurred to them to put it in these terms. There is definitely a correlation, but not causal.
Didn't Lorentz like implicitly understand this, because like his whole ether theory is consistent with this viewpoint that, you know, the change in internal duration, the difference in internal durations is caused by a difference in motion through the ether.
So that's okay. So that is the cause. That is a correct statement. But when you look at what value that is to humanity, like what actions can humans take to make that happen? Like that's one of the reasons why we come up with causal relationships in the first place, is so that we can come up with a vision that we like and interact with reality and achieve that vision, so we can cause it to happen. And you can't really do that by just saying change speed. What you're going to end up doing is doing specific work, right? That's the input humans have. Is I'm going to accelerate something over some distance to achieve the speed necessary to achieve time dilation. So it's in some sense it's a more human focused cause where speed is an intermediary. Like our handle on this is the specific work humans do, and that's our
speed. Yeah, a change in speed is indeed the intermediary between man's action and a change in durations. Mm-hmm. But if we're interested in identifying further physical causes,
yes.
Shouldn't we be concerned with the proximate cause, that is like the more immediate cause, which is this change in the difference. The change in the duration of the process is caused somehow by the change in the speed with respect to this preferred frame.
Met all the same wickets that specific work did for Mill's method. So yes, I mean speed did. And another parameter that we haven't even talked about, which is the average effective speed of light, also met all the same standards that these met. So like if you were to create like a causal chain from human action to what's happening in this framework, we do work which causes a change in velocity in the preferred frame, speed, excuse me. And then that changes this term that I'm calling the average effective speed of light, which is the average effective speed of light relative to the object or the system under consideration. And so and then this is what directly causes, this is the most immediate cause of time dilation under this framework.
So let's see. So far we've discussed how we didn't go like too deeply into the details, but we've discussed how your paper shows through Mill's methods that a change in speed with respect to the universal stationary frame is the cause of the change in durations of internal processes.
Yes.
Now you're going further and you're saying that the way that the change in speed changes the duration of those internal processes. Yeah, I like this. Yeah. I like this. what you've written on the board here. The way it does that is via a change in the average effective speed of light.
Yes.
The change in motion with respect to the universal stationary frame, causes a change in the average effective speed of light for that body, and that causes the body's internal processes to unfold slower or differently at a different rate.
Yes.
Okay, so let's see. Tell us first what the average effective speed of light is. It's
So
a very
average-
it's a different kind of concept than what's usually thought about. It's
the
because
average-
it's not the speed of light that's supposed to be constant, and because you don't think the speed of light is constant. It's not the two-way speed of light, which is sort of what a lot of people would probably use as like a base fact if they don't think that the speed of light is constant. What are you talking? What is this average effective speed of light you're talking about? It's neither of those things.
So let's I guess it's when you talk about speeds, it's always relative to something. So
Yes.
the speed of light relative to the preferred frame is constant. That's c. And it's
Okay.
the same in all directions. Doesn't matter which direction it is. Now, when you have an object, let's make it a different color here. When you have an object, I don't know if that comes up as green. It has some velocity. Okay, the speed of light relative to that object isn't constant anymore. You have in the y dimension. So like if you then shift your frame now, you're in this velocity frame. You're measuring velocity up and down this way and over and this way. If you had calibrated instruments, this is what Lorentz had to do to come up with this Lorentz transformations. By the way, this was a process he went through. This when you stretch this out from the fixed frame to the preferred frame, light is actually bouncing like a sawtooth this way, right? It's going up and it's going down. Okay, so and he's only measuring the y component. That's this.
You're talking about the Michelson-Morley experiment right now?
Yes, so you can leverage
With light going back, so light's going back and forth in the frame of the experiment, but from the preferred frame, it's traveling forward in a zigzag pattern.
Yes, so if you perform the math that Michelson-Morley did for the y direction, the speed of light in the I'm gonna use green to reference the value measured in the frames fixed to the moving object. Okay. So you have this speed of light in the y direction is actually equal to the speed of light, but it's over gamma, 1 over gamma v. So it's slightly reduced. This number is this 1 over gamma v. This number is between 0 and 1. So at the speed of light, this becomes 0. That means the y value is 0 at that point. It's not going up.
Yep.
And so when you look at the x direction, it's actually worse than this. It's 1 over gamma v squared. And so the speed of light relative to this object isn't even isotropic in terms of the average two-way. There's a difference between the y direction and the x direction. No, this is the average.
Oh, holy moly!
This is the average. This one actually happens to be the same in both directions.
Dude, I didn't realize this. When we talk about the two-way speed of light being constant, that also assumes a bunch of baggage from special relativity.
Yeah, you have to. You have to get rid of all
See,
of
this
that.
is why I want to reinduce everything, because all this stuff it like sneaks into your thinking. Apparently, it hasn't snuck into your thinking. Apparently, though I'm a little.
No. I stumbled through all of this. Every single one of these realizations you're making, I made the mistake of not cleaning the household, the conceptual housekeeping.
Yeah.
I failed to do. And
right, but
so,
you've done it without reproving all of physics, which is my plan. So it makes me, it makes me wonder how, especially because it's so hard, it makes me wonder if I really need to do it. But go on.
I don't know. I think it could be helpful to go from soup to nuts, like having a corpus of human knowledge validated that way. I think your project, if you finish, is going to be so huge that it would require a database and an interface that would make it efficient.
I'm also doing it for reasons other than just this rehabilitation of physics. It's also just my vision for how knowledge should be structured.
Yes. And this is assuming that the velocity is only in the x direction. There's some built-in assumptions here. Hopefully you're
Yeah.
already somewhat familiar with relativity, so it's not a big problem.
So
But
if you assume a preferred frame,
so this
if
is
yeah,
yeah, if you assume a preferred frame, these are the actual calibrated measurements of the speed of light, the average. You could figure out the the speed in one direction. And so like if you actually did it directionally, let me put it over here. So the speed of x, and it's going in this direction, is going to be c minus b, I think. And then if you're going in cx in the other direction, I think it's c plus v. It's just like the
yeah,
Newtonian
yeah,
Galilean relativity type stuff. And then the idea is, well, you have to take the average. Well, the average isn't straight add and divide by 2. You actually have to average over time. And it takes,
yep,
it's in this state a lot longer than it's in this state. This state
yep,
doesn't happen as fast. This state happens a
yep.
lot. This going this way happens a lot
And
faster.
so it's a net slowing.
Yeah, so it's a net slowing, which is why this one gets a gamma squared here.
Yep.
And they're not the same. The average effective speed of light is isotropic, the two-way average. And so why is that? Well, if you have two entities separated by some distance, delta x, in the stationary frame, when it's moving, length contraction occurs, yes?
Mm-hmm.
So that means the time it takes for light to go from one end to the other is reduced. It requires less time for that to happen. And so there's an effective
Wait a
increase.
second. Wait. Let me hold on a second. You're saying that like space itself gets shortened, not the length of some particular entity? Okay. Start
I'm not
over
convinced
with
that
this
space-
again.
I'm not convinced that space is a material thing.
Of
This
course.
is
Yeah. That's why I was calling. That's why I'm skeptical with
This is-
skepticals.
the distance between entities. So,
Uh-huh.
like I think Dirac came up with a very good explanation for why the electronic field flattens, which that was a good description, I think, of Fitzgerald's argument.
Yeah.
For Fitzgerald's length contraction. So I think, I believe that happens. For one, it's consistent if you believe in the eternal simultaneity and a preferred frame, and then you have to integrate also that with the Michelson-Morley results. The contraction has to happen so that because of this extra retardation in the x direction, the light goes in the x and comes back and then reunites with the y at the same moment, right? And in order for that to happen, it has to travel less distance so that it can account for the fact that it's a lot slower. So this ends up being contraction. So let's just make this one.
But this contraction is a result of the fact that both of these blue lines are mounted to the same one entity, the same one body. The body contracts, not the space between them contracting. Yes. Okay, very important. Okay, I didn't see, you didn't draw the body connecting the two blue poles. Okay.
Yeah, this is the body here and the body here. Let's say it's a particle.
Well, but it's one body. It's one body that joins the two poles, like the Michelson-Morley table.
Well, I guess it's the distance between two bodies.
But my point is that the distance itself doesn't contract. The body that is the mounting for both of these blue poles. So I like, you would agree we should draw a horizontal line connecting your two blue dots, right?
Yeah.
Or maybe below it, depending. Yeah, right. So like that body you just drew, that contracts, and now the two poles are closer, right?
Yes.
Okay, just making sure we're on the same page. That
yes.
the body contracts, not the distance between bodies per se.
Well, the bodies get closer. There is no. Let's say
the bodies get closer, but not because the distance is contracting. It's because the body connecting the two detectors is contracting.
Maybe the body moves, like something. I don't know exactly the mechanism involved with the shrinking of the space between them, but it's not the space isn't a physical thing. Space is a measure of.
Yeah.
And maybe the bodies move. Maybe there was one move closer to the other. I don't know.
Your audio got quiet.
My audio got quiet. Is this better?
Now it's good. It just suddenly got better. So say that again.
So I don't know why the distance between them shrank. It's definitely not space itself shrank.
Well, I think Lorentz gave us a really good hypothesis about that. The internal forces. I mean, you described this, dialect Fitzgerald. The internal forces are altered because they're moving through the medium that mediates those internal forces, and so the internal forces are altered, which causes them the parts of the body to get closer to one another.
Correct.
Yeah.
And so,
although that's a hypothesis that's a really good hypothesis, but it's separate from all of your work.
Right. And so when you account for this shorter distance between them, the effective speed of x changes by a factor of gamma. It gets okay. So then you get this. Let's just call it. I'm going to erase this and put cx0 underneath it. Okay, so cx0 average is equal to c over gamma v, and which is the same as the cy value. And so this ends up being like the effective speed of y is the same as the effective speed, or the same as the actual speed of y, but the effective speed of x is different between these two by factor of gamma. Because the distance that light has to travel is less, so it takes less time for light to reach from point A to point B. And so this is a very important term, and the way I stumbled across this was actually sort of like not exactly like my whole discovery process hasn't been linear. It's been bumbling along, but the way this has a very important causal effect on the entire framework, and that is the speed of light has been said to be the speed of causality. If it's the intermediary of all interactions, then if the actual rate of the back and forth between the mediation, so you have let's say entity 1 and entity 2, and then in between you have this light going back and forth and mediating between them, creating these like closed circuits, let's say. If this value, this C naught value, the effective speed is changing, so let's say it takes 1 billion for your steak to reach medium rare, and if you were to slow this down, it takes longer to reach 1 billion, right? Relative to a C that's the same within the preferred frame. So this becomes the speed of causality relative to the system we're engaged or considering at that time. So that's a very important parameter. So yeah, that's I guess that becomes the cause of time dilation. So we just talked about kinetic situations, but this also is true for the gravitational context as well. This extends into gravity. And in fact, when you start translating this into specific energy terms, it becomes the actual cause, variations in this value become the cause of gravity. And I'd like to talk about that if we have time.
Yeah, we do have time. Let me make sure I understand what's being said so far. And please correct me if I'm stepping a little bit outside of what you think you've proven here. And incidentally, I've read your paper. It is very convincing. I need to read it very closely to see if it's exactly proven. And we'll discuss at the end what I think the advantages are of what's being thought about here. So here's my summary. You've shown that a change with respect to some frame, we know not what, causes a change in the internal duration. One reason this could be the case, and this part of your theory it seems like is a hypothesis. One reason, so that earlier part you regard as proven. This next part is a hypothesis that the speed of light could be moving isotropically with respect to the universal stationary frame only. And as a result, the reason that a change in speed with respect to some frame, this universal stationary frame, the reason that a change in speed with respect to this frame causes a change in the duration of internal processes is because internal processes are mediated by physical processes that travel at the speed of light. And if the object's moving with respect to the universal stationary frame, which is the frame in which light actually moves isotropically, moving with respect to that frame changes the effective speed at which internal causal processes unfold, thus causing the duration dilation. Is all of that accurate?
Yes, I think that's a very accurate way to put it.
Okay, cool. Even the part where I said part of it's proven and the other part's a hypothesis?
So, I'm trying hard to demonstrate everything, so there's always a chance I might have misstepped or taken a leap I shouldn't have. So, that's what peer review is for. And, you're the first person to have peer reviewed the paper, so I appreciate the feedback.
Well, my question was, am I right in thinking that you regard your Mills methods identifying the cause of duration dilation, you regard that as proven? And I'm pretty close to regarding that as proven also, by the way. I'd need to just review the paper a little harder, and then I would think you proved it, actually. It seems to me, though, that the latter part is a hypothesis, because you're making the completely reasonable hypothesis that light moves isotropically only with respect to the universal stationary frame.
Yes.
Okay. So everything that follows from that is now a hypothesis, because I don't think you don't prove that anywhere, and I mean, if you did, you'd get a Nobel Prize.
Well, I think the preferred frame is the frame in which light is isotropic within it. I don't think that that's in question.
Well, what's your proof of that?
Well, when light leaves a distant source, let's say like a supernova, it all arrives at the same time. So that suggests to me that all that light is traveling at the same speed with respect to the other light. There's no measurable delay. And if light didn't move the same speed relative, whatever the speed that was going is static, then I guess that logically leads to the conclusion that in one frame, it would be isotropic in all directions, I guess. So, like,
how do you know that's the same frame that movement with respect to causes the time dilation? How do you know it's the same frame?
Because if the speed of light with respect to the object is what causes time dilation, then there is a frame at which time dilation is smallest.
Of course, but then how do you know that speed of light with respect to the effective speed of light with respect to the object is the cause of time dilation?
So this was required another experiment, like a Mills method type of experiment, where you now bring in gravity. So if you have like a planet here, okay, and you have different distances around this planet, and let's just make two distances. We'll make one at infinity and one at r, okay? And you have an object that's stationary here and here. General relativity describes, I think, what's going to happen very accurately. The time dilation experience at r is different than at infinity. Infinity is, if it's in this universal stationary frame, is going to be 0, and then r is going to be a greater experience. Things are going to slow down. So here's a case where you don't have any velocity with respect to the preferred frame. And so while this was true in the kinetic case, it's not
any
true
change in velocity with respect to the preferred frame.
So, yes. Yes. So here's a case where there is no change and with respect to the preferred frame.
And there's just a change in position with respect to an object.
Yes. And you now have time dilation. So really, this is a special causal chain that actually looks more like this when you take into the general case, where you take in gravity. if you look at Schwarzschild metric, and you look at the coordinate speed of light, it reduces the closer you get to the gravity source. So like the speed of light out here, and I'll call it CR, for going this way versus this way, versus the CR here. Well, let's just call it C infinity, actually. So
how do you know that's true, though? So you're saying basically, so here's what I'm gathering. Let me make sure I follow you so far. You're saying that in the case of gravity, there is no change in motion with respect to the universal frame. But for these two blue dots, there is a change in position with respect to a planet. And a planet causes, and different distances from a planet cause a difference in the effective speed of light for that entity, which will then cause a difference in the rate of its internal processes. Okay, but how do you know that the planet causes a difference in the speed of light at different locations? Let me tell you my motivation. I'm really interested in the reason I find what you're writing about here so compelling is because it seems like you may have actually proven something, as opposed to, say, like what Henry and Chantal have are really enticing hypotheses about the nature of the ether. And I think that's really great. But none of it's proven. It's just hypotheses that are consistent with the observations, which methodologically, if we leave it just at that, methodologically, it isn't any better than what we already have. It's just this guess. It makes more sense metaphysically. Like, you've eliminated the dumb metaphysics from relativity, but you still aren't using an inductive methodology to prove it. What I find enticing about what you have is that it seems like you've been very careful to only include things that you regard as certain. So that's why I'm really hounding you on this. How are you, so getting back to the question, what makes you certain that the speed of light is different for these two different blue entities in the vicinity of the green planet?
So they have different experiments that have run. The Shapiro light delay experiment is an example where they shined a light to Mercury and back, and the sun was in the middle. Okay, so you had the sun in the middle.
Whoa.
And you had, I think it was microwaves, but still light.
Yep.
It's not visible light. And then you had like Earth on one side and Mercury on the other, and you shine light there and back. And they calculated what it would take if light were constant through there, and then to go there and back. So this is measuring an average again, but still, what we're concerned with is this region right in here, where it's close proximity to the sun. If it slows down here, it should take longer, and that's exactly what they found. They found that it took longer for light to go through that region, to do the round trip, and the conclusion was that it slowed down near the sun in accordance with general relativity's formulation. So general relativity, I guess if I had to put it as an analogy, general relativity is Ptolemy's model of planetary motion around us. And I don't want to say I'm Kepler. I think I'm closer to Copernicus, where maybe I come up with a slightly flawed model where the sun is at the center, which is correct, but I say circles in terms of their motion. Maybe that's not.
Yeah, you're not getting all the details right yet. Maybe, yeah.
But the sun is the cause, and you're taking a non-causal model and translating it to causes. I'm trying to do the same thing that Copernicus was doing. Maybe a Kepler will come after me and make it better, and then maybe a Newton.
No. You should be Kepler too.
Okay. Well, I'm trying to stay feasible here, with what I've at least I've achieved this. I don't know if I'll achieve the next step. The next step is figuring out what is it about the sun that causes the region around it to slow down the speed of light, and that's actually a quantum question. So that becomes like an opening to a quantum theory of gravity. Is like, okay, what is it about the quantum nature that's going around there that's affecting the quantum object, which is light, in a way that slows it down? And another way to put it is, what is adjusting the permeability and permittivity of that space around there, which we used to think was constant, but is not constant in this framework. And it becomes a question we can start investigating. Like, we can start looking into it.
When I think of quantum, I think specifically of the nature of the ether there. At that point, making inferences about the nature of the ether might help us there.
Okay. So, I finally got an answer to your question. Why am I certain about this? Because when you measure the speed of light at any of these locations, at this location, your measurement says it's constant.
Yep.
Okay. But if you're time dilated, then your measurements are wrong.
Yep.
And when you calibrate
your measurements are affected, but yeah.
Yeah. So when you calibrate it, so you're measuring this, let's say dr dt. That's your uncalibrated measurements, right? But you want to say, well, what's the relationship here between this and the actual coordinate speed? And you see that when you say that, okay, well, this is c, then at least in the r direction, what that means is the speed of light in the r direction is 1 over gamma g squared, much like it was in the velocity direction, the kinetic case. Like there's a somewhat of an analogy here.
Yeah, I think you already convinced me when I just thought about this Shapiro experiment. Like it's just like normally we measure a certain two-way speed of light, but in the Shapiro experiment we measured a different two-way. We measured a slower two-way speed of light. Why? Because the light got sped up as it got sucked into the sun. Then it slowed down as it was moving away from the sun, and because it spent more time getting slowed down, the overall effect was a slowdown. Isn't that what's going on there?
So we don't know that the speed of light is speeding up. It's actually slowing down.
That's what I'm saying.
Okay, you said it's
No, I'm saying it's I'm going into the realm of hypothesis here that it's like the Michelson-Morley experiment, that on the way past the sun it's speeding up, then on the way away from the sun it's slowing down, then on the way coming back it's speeding up again.
So if you believe in the ether flow theory, that would be the reason for the delayed effect, because it's creating the same kind of thing as a Michelson-Morley. But if there is no ether, if there's nothing being sucked in, if it's just the light is slowing down, it could either be slowing down because it sped up and slowed down, or the whole thing slowed down. We don't actually know.
Yeah, all we know for sure is it took longer. That I shouldn't have gone into the hypothesis.
Average is slower. We don't know why
the average is slower. Right, but like the only way the average could possibly be slower is if it slowed down at some point in there.
Yes, that's right. Yeah.
Yeah, and all of this. Yeah, so getting back. So I'm as convinced as I can be in a quick conversation of this, that the light actually gets slow. This
is getting into like a variable speed of light approach to gravity, and I'm not the first one to come up with this. I mean, Einstein.
Yeah, of course.
Was the first, but there's like there's actually a significant standing of physicists today that are looking into variable speed of light theories and things like that.
Yeah. And one thing that I like about this is you're not making particular claims about the ether, that it's like, different densities or it's getting sucked in, but, you're just saying the speed of light is different, and what I would add to that is I think the ether is proven, and I would say, well, I mean, I think there's probably a way to give yourself to make a series of inferences that can be made with certainty that lead you to not only your theory, where the speed of light is different at different locations surrounding a gravitational body, but to identify that the cause is that the gravitational body is affecting the ether somehow. Because, I mean, like, light is a wave of the ether. There's an ether, and light is a wave of that ether. I think that's proven in one of my videos. I think I would need to formalize this argument, but I think it could be proven that gravitational bodies are doing something to the ether to alter the speed of light at those locations.
It's doing something. I mean, you remove the body and
it's doing something, but I would go further and say it can be proven that it's effectuating that by doing something to the ether. I think you could prove that.
Yeah, maybe. I mean, I hope someone proves why. That's the next step, obviously, is to figure out why that's happening. But just like Kepler found out that the sun was the cause of planetary motions, but he didn't know the mechanism in terms of gravity. It wasn't until
Yeah.
Newton figured that out. But then Newton only took it so far. He had like an action at a distance. So he's like, why is this thing way over here affecting this thing way over here instantaneously? Like, it makes no sense. Like, your concept of locality has to hold. And then finally, like, this theory that I've developed actually takes it to the next step and finds the local mechanism involved with what is it about gravity that causes the thing to gravitate towards it. It's an internal mechanism.
That's a fantastic segue. Let's talk about that now.
All right, so the internal
So
mechanism.
this is the next, and this is the next part of his paper. So you can read all of this in the link in the description.
Yeah, this part actually, if it isn't in the paper, it will be eventually. I had it in an earlier version. I took it out. I'm going to put it back in. But it was, you were wondering like where this idea of internal specific energy came from. And so time dilation, the slowing of processes, could be considered as an effect of a reduction in motion inside the object. And so motion being another way to measure it is in terms of energy, specifically specific energy. Now you might be able to see why I'm calling this theory universal specificity. It's nothing other than like the universal eternal where you have basically it's the specific forces and these specific energies are like all over the place. And what's good about this is that you eliminate the concept of mass, which is overused to apply to both quantity of matter and resistance to motion changes. And so they're really, it's a coupling of two concepts you need to take separately. And that would be another branch you could take my theory into is, okay, let's take the specific nature, which removes inertia and the quantity of matter, and then integrate it with that. But that's a future thing. So internal motion, it came to me from the fact that I was trying to relate this to energy. So Feynman did a very similar derivation when he came up with like energy, Einstein's equals mc squared. And I'm like, well, let me do the same kind of thing in my derivation of specific energy, where if you rewrite this, it turns out that this 1/2 c squared is equal to 1/2 c squared over 1 over gamma. This is a velocity in the kinetic case only. And then you have this other 1/2 v squared. Okay, so I'm saying that this is in my earlier conceptions, this is total energy. This is your internal specific energy, and then this is your kinetic energy with respect to the preferred frame. And one of the things I noticed was that as the object sped up, the internal energy reduced to the point where the total was constant. And a lot of people, when they derive the time dilation equation, they do this. So this is the velocity of the frame, this is your speed of light, and then this is your c naught, which is what I'll call this. And
they do their own version of this. You've made this.
Okay.
Yeah.
Right? And they say they create a relationship between all of these. Well, the speed of light in the y direction relative to the moving frame is this squared value, and then for the area, and then you have c squared, and then you have vp squared, right? This is the Pythagoras theorem.
They do their own version of this, right? None of it,
and it's still true, right? So this is coming up with 1/2 all around, and that's what you get here. So this term, like I was trying to this term always came up like, what the hell is this? It turned out that this is the exact same value as the average effective speed of light squared. So your internal energy is a function, your internal motion is a function of this c naught value. When you take this energy model into account. So that was where the idea originally kind of was born. I don't know if that's the right way to validate it, but this internal energy value, so this EI, right? So this E sub I is equal to 1/2 c naught squared, which is half c squared over the gamma squared for velocity. there is a direct relationship to measure c naught squared, and that is when you look at the space time interval in relativity.
I have a question, which is this blue equation on your left, or is that your right? On
This one's on my
yeah,
right.
that one. That's okay. Yeah. The blue equation. Where did that come from?
So this equation is just the Pythagorean theorem to figure out what the speed of light is from when you look at the Michelson-Morley-like experiment for the y component. It's what leads to this equation too, as well. Like it's one derivation I've seen where you have the speed of light measured from the coordinate frame that's not moving, and then this is also so relative to the object, and then this is the speed of the object.
Okay, this is vector addition. This is friggin'
okay.
vector. It's like wind
Vector
speed
addition.
plus airspeed equals ground speed.
Yes. Yeah, this is vector math. Okay. I don't know if you want to go into more depth than that, but this is...
No, I do not. I do not. I just didn't realize it was that simple. Okay, yeah.
So I realized that so this is in terms of specific energy. This is the kinetic specific energy. This is the total energy of the system, and then this thing was like equivalent to internal energy. And Einstein had a very similar model where he had E equals mc squared times gamma is equal to, let me see if I can write this down. E equals mc squared times, I believe it was gamma, and then that's like m naught c naught squared, and then you have the gamma minus 1, and then m naught c squared, and that's like the kinetic term, and then that's your internal energy term, and that's your total energy. This is analogous to that. So you have your total term, your internal term, and then your kinetic term. And this is just measuring motion, not energy, motion. So this is the total motion you get from the speed of light. And its components are, because you have a moving frame now, you have your kinetic part and your internal part. All right? And so this internal motion, I realized, had a gradient in gravity. There's an analogy for this when you want to use a space-time metric. If you want to see like what relativity would be if you mapped it over into these terms, you have this space-time interval ds, okay, squared is equal to some, depending on your metric. Okay, when you take this with respect to time squared, so you have two. You basically have two of the. You have the ds to dt. This is equivalent to the average effective speed of light squared. So if you want to look at any of the relativistic terms and map it over to this, you just take this space-time interval with respect to time squared, and that's this squared, and it gives you, and then you can take the 1/2, obviously, and then that gives
your
you
equation,
your energy.
The equation on your right is just your way of writing the mainstream equation on your upper left.
So I don't know how the viewers are going to see this. This equation here is the mainstream mapping to these values. So like
no, but the mapping maps the E equals mc squared equation to your specific energy equation, right?
So
on your upper
I see. Yeah. This E equals mc squared. This is just an analogy. So like
okay, it's not actually the same way of writing.
You can't just like, okay, let's divide mass and get the same answer, because you're integrating mass with this one. You're not integrating mass with this one. That's what made it so easy to work with, because when you start integrating just acceleration with distance versus now you're integrating mass and acceleration with distance, like this term is changing, right?
Oh yeah, mass is changing.
This isn't changing, so this is a lot easier to work with. So it's not exactly like you can't just divide mass out, because mass, while you're integrating it, the whole integration is changing. So it's not as simple as just dividing out mass. But in terms of the model, it's the same model. It's just in terms of specific energy, where you abstract away mass and inertia together, and this one includes mass and inertia together. It's just they're two different equations for two different purposes: measuring motion, total, inside, and relative to the preferred frame, This is measuring energy, total, inside, relative to the preferred frame. Energy, different than motion. Okay, so energy is the ability to do work. This is just specific energy and specific work.
Yeah, this is this is specific energy, specifically the ability to change the speed for a particular object.
So I don't even think that necessarily holds. Just because you have some specific energy doesn't mean you have the ability to do some specific amount of work. Because
no, but it's specific energy. Yeah, that's what I said. It's like it doesn't have to do with work. It's just the ability to change the motion of some specific object.
Yeah, if they happen to have the same mass, I do believe they do have the ability to do the same specific work to that object.
Okay, so I guess I shouldn't say it's like, I shouldn't say that it's the ability to cause a change in that motion.
It's just a measure of change in that motion. It's just a measure.
It's a measure of the change of the motion of a specific object.
Yes. Yeah.
Yeah. Okay.
So this is more causal power than this. This is more of a description of what's happening inside.
Okay. So how does that lead to a gravitational force?
I'm glad you asked. So I learned that when you start looking at a massive body, let's take green here. Okay, and you have distances around it. We'll draw R1 and R2 being infinity and R. Okay, the actual internal energy is different. At infinity, it equals E max.
Mm-hmm.
And this is again stationary with respect to the preferred frame. All right, and then you have another point at this point R here, also stationary. Its internal energy, specific energy, is not E max. It's something less than E max. Okay, and my paper goes into details on the quantitative nature of all this, but that means there's a gradient. That means so gradient just means taking the differential of some entity, in this case I, over some length interval, in this case R. This is non-zero.
Yep.
That means the motion description of motion inside objects in gravity fields is different at different altitudes, let's say. So my head is at a different motion state than my feet. It's moving more. There's more internal motion than at my feet. And if you run the numbers, because it's almost like a internal energy is almost like a potential, like it's my capacity to act. So if you go to one end of the extreme where you're going the speed of light, or you're near an event horizon, EI is zero. You have no capacity to act. You've ceased changing. Okay? There's no more action involved. Versus when you're stationary in the frame, that's as much as you can possibly act. Okay, so there's like a potential for action involved with this description of internal energy. And so it becomes a potential energy term, and the paper goes into more detail about this. And so specific forces are defined as negative gradients, which is what this whole thing is doing, of this internal of potential energies. But in this case, E sub I is a potential energy within the object, its own ability to act.
And specific forces are just accelerations.
And specific forces are just accelerations. So this describes how you would mathematically measure or estimate the acceleration of a body based on its internal energy gradients. And if my paper goes into detail, but if you do the math, it's just as accurate. At least I proved it in a special case as relativity when considering objects at rest and then let go. So that much has been shown. I think a mathematician needs to kind of come in and generalize it for all cases. I'm trying to do that now. That's kind of like ongoing work. But at least for the simple case where the the coordinate acceleration in Schwarzschild metrics is gm over r squared times 1 over gamma g2. That's the gravitational acceleration if you measured it infinitely far away using calibrated instruments. And so that's like your d squared r over dt. And this method predicts that value exactly. So, and this value changes in the Schwarzschild metric when you're not stationary, when you have some velocity. and I'm working through the process. Like now you're getting into differential geometry, which I'm having to train myself on,
Mm-hmm.
and because you're dealing with a lot of like a lot of unit changes, a lot of because like you're this is actually anyway. I don't want to get into too much detail. I think that's enough
Yeah,
detail
yeah. So
for this.
I think that's good. So that is a very so the takeaway I'm getting is this. Um, within individual particles, there is a specific energy gradient as a result of the average effective speed of light being different values in different locations of the particle at different
Yeah.
parts of the individual, and as a result this leads to a acceleration on each individual particle, which would account for this uniform so-called force of gravity.
Yes.
Yeah.
Okay. So we've taken gravity only so far to this point. We've done something slightly better than what Newton had, which was action at a distance. We've now made it to a local action. There's this gradient inside an object, which is caused by the average effective speed of light gradient. And so then the next question is what is it that causes that? So that's like the next step in the causal chain of reasoning. And who knows who's going to come up with that? I'm going to be working on it, but it doesn't have to be me.
Yeah, well, maybe it'll be someone in our audience. So I like a lot of this. Some of it we've chosen not to include because I wasn't convinced of it. I think it's stuff you need to flesh out a little bit more in the paper. But I recommend people read the paper, and you can answer in the comments, and tell me what you think. Do you think Dan proves his case here? And something that I'll add is that I think what I see is the real promise of this. I've been focusing a lot on the ether. But that doesn't mean, just because there is an ether and just because it is central to so many things that are happening, those are both true. Those are both certain. It doesn't mean that that's the next step. It doesn't mean that that's the place we need to be looking for necessarily for new progress. It's certainly one of the places. But what Dan here has done, if he's really succeeded, if all of the reasoning steps check out, and I need to read it more carefully to see if I agree if the reasoning steps check out. And I'll be continuing to read Dan's paper here to make sure that they do, because I think this has real promise. If the reasoning steps really do check out, then what we have here is not just a hypothesis. We have a set of steps that are really understood with certainty, something that we can draw from the observations all the way to certain results, which is specifically, what's causing this change in time in the internal processes. It's a change in speed with respect to some frame. That's solid progress. That's a solid rehabilitation of relativity theory, is maybe the word you can use. Taking the theory and the things it gets right, and then rehabilitation is the wrong word, because we really need to throw out relativity theory. But it's just a complete recasting of these phenomenon, and not unlike Lorentz ether theory. It's not recasting them in terms of some kind of hypothesis. It's recasting it in terms that we already are certain of. Now hopefully that sets the stage for learning more about the ether. But this is how science proceeds. It's not up to us the next step that we're able to take. It's up to reality and what we know about it and what we don't know. And I think Dan has discovered a really promising new route. So I really encourage you to read his paper. Dan, any thoughts before we let you go today?
I suppose I'll leave with that we're left with, just to your point, it's what we have available to us in the present that allows us to take the next steps into the future. So I think you summarized it pretty well. So thank you for having me.
Yeah, thank you, Dan.